I've looked at a number of the Planck units, mainly comparing them to other things, and it was lots of fun. But now I want to look at where these units come from and how they came to be derived. Let's find out more. This is actually going to be a really mathsy video, and because I always want to make videos accessible to everyone, I'm going to spend the first part of the video explaining some of the mathematical conventions that I'll be using. I've put chapters in, so if you understand the maths, you can skip forward to the chapter called Why Do We Need Them? Let's get on. So let's have a look at the maths conventions I'm going to use, and I'm looking here really at 5 ideas that will help us understand the maths that's coming up. Idea 1 is all about units that we use. Let's think of speed. One way of recording speed is as meters per second, and this will be written like this, with a slash between the meters and the seconds. Speed is calculated by dividing a distance by time. For instance, if I'm in my car and I travel 100 meters in 10 seconds, I can find out my speed by dividing the distance by the time, and that will give me a speed of 10 meters per second. If you look at the calculation that I made, it was meters divided by seconds, and the speed is in the units of meters per second. So these two ways of writing things are in effect the same. So this and this are actually the same. Meters per second really means meters divided by seconds. Idea 2 is all about indices. Now in algebra we often use letters to represent numbers, so I'm going to use the letter A in my example here, but the A could represent any number. A squared really means A multiplied by A. A cubed is A times A times A. And A to the power 4 is A times A times A times A. So what about just A on its own? A on its own really means A to the power 1. We never really add the 1 because there's no point. But always remember that the 1 is always there. We just don't write it. Idea 3 then asks, so what about numbers that are raised to a fraction? For instance, what is A to the power of a half? Well, A to the power of a half is actually the square root of A. This would then mean that A to the power of 3 over 2 is the square root of A cubed. Idea 4 is all about negatives. In the previous idea, all the powers that we looked at were positive numbers. But what about negative numbers? What about A to the power of minus 2? This actually means 1 divided by A squared. I can always bring the A up to the top here, but in doing so I change the sign on the power. 1 divided by A, therefore, putting these two ideas together, is actually 1 divided by A to the 1. And then by bringing the A up to the top, this is then A to the minus 1. Acceleration is a change in speed and so is measured in meters per second squared. This is meters divided by seconds squared. And by using all the ideas we've studied so far, it means that meters per second squared is actually meters divided by seconds squared. We can then bring the S up to the top, but have to change the sign. So another way of writing meters per second squared is ms to the minus 2. And this brings us to our final idea before we continue. And this is that a to the power x multiplied by a to the power y actually equals a to the power x plus y. And using our previous ideas, this actually makes sense. If you think about it, a cubed multiplied by a squared really means a times a times a times a times a, which is a to the 5, which is a to the 3 plus 2. Okay, I hope we've got that. Let's continue and think about why we have the need for the Planck units. Well, let's think about time. The SI unit of time is a second. But humans came up with the concept of the second. It was historically measured as a fraction of a day on this planet. And even though we've now redefined it to a great degree of accuracy, it's still related to that ancient measurement. The same goes for all our measurements of length, temperature and mass. So wouldn't it be great if we could find some way of defining these measurements that isn't reliant on human-made values. And this would then transcend our human values. So can we define length, time, temperature and mass just in terms of universal constants? There are a number of fundamental constants of the universe. Some of these are the speed of light in a vacuum, which is represented as the letter c, the Planck constant, or rather the reduced Planck constant, and this gives a relationship between the energy of a photon and its wavelength, and this is represented as h bar like this. The reduced Planck constant is just the Planck constant divided by 2 pi. Also the Boltzmann constant, which relates the energy of particles in a gas and the temperature of the gas. And finally we have the gravitational constant. There are more, but these are the ones that we're interested in today, and actually we'll also see later why we can ignore the other constants. The Planck units is kind of an attempt to make all these constants equal 1. This would mean that we could then rewrite all the equations of physics and have these values as just 1. That would make our physics much easier. So, can we define length and time and temperature and mass in terms of just these constants? So in order to do this, we're going to perform something called a dimensional analysis on these constants. And to do this, we're going to look at each of the constants and explain them just in terms of length, which I'm going to represent as a capital L, or time, which I'll represent as a capital T, mass, which is represented by a capital N, and temperature, which I'm going to represent by the Greek letter theta, because T's already been used up. In doing this, I'm only interested in the dimension, so meters, miles, and so on would all be length or L values. Also, because constants are dimensionless, I'm going to ignore them, and I'll explain what I mean by that when I get to one. We also tend to put square brackets around these dimensions, if for no other reason it means I'm not going to get them confused with other values. Let's then have a look at these constants and see if we can do this. Let's start with h bar. So h bar is equal to 1.054 times 10 to the minus 34 joule seconds. So let's forget the numbers and just look at the units. So that means that's joules multiplied by seconds. The second is a unit of time, so I can replace seconds with our time value. Now the joule is a measure of energy. I then need to find some way of representing energy in terms of just length, time, mass or temperature. We can replace joule then with another measure that means the same kind of thing. One way of representing energy is to say that E, energy, equals half mv squared. So I can replace the energy term here with half mv squared. Again, the half is a constant and has got no dimension, so I can ignore it. M is mass, so I can replace mass with my mass term capital M. And velocity is distance divided by time. Distance is a length, and time is a time. And because I squared v, I need to square both these terms. My dimensions for h bar are then mass multiplied by length squared, divided by time squared, and then multiplied by time. This time here will cancel with one of the times here, and so our final dimension for h bar is ml squared divided by t. Rearranging it slightly, we have ml squared t to the minus 1. Now let's look at the gravitational constant, and that's 6.67 times 10 to the minus 11 meters cubed, kilogram to the minus 1, seconds to the minus 2. Meters cubed is a length cubed, kilogram to the minus 1 is a mass to the minus 1, and seconds to the minus 2 is time to the minus 2. Next on to the speed of light, and this one's quite easy. The speed of light is 299,792,458 meters per second, which is, by bringing the s up to the top, ms to the minus 1. This then is our length measurement and time to the minus 1. Finally, on to the Boltzmann constant, 1.38 times 10 to the minus 23 meters squared, kilogram per second squared, Kelvin. Rearranging this a little, we get meters squared, kilogram, seconds to the -2, Kelvin to the -1. This then gives us our length measurement squared, multiplied by our mass measurement, multiplied by time to the -2, and temperature to the -1. Now that we've given ourselves a set of dimensions for each of these constants that we're using, we're now going to try and define length, mass, temperature and time in relation to just these constants. Let's start then with length. We're now going to say that length then equals h bar multiplied by g multiplied by c multiplied by kb. And each of these values might then be raised to a certain power. And I'm going to call these powers w, x, y and z. We now need to find for each of the Planck units what the value of w, x, y and z are. I'm going to go through each of the Planck units and do the maths for each of them. I'm going to start by looking at the Planck length. Now I've tried writing a script for this, but it just looks a mess. So I'm going unscripted now. I've got my maths in front of me. I actually did the maths myself because it makes more sense to do it myself. It helps me to understand it. Okay, so let's see how I can do without a script. Firstly, I want to say that L is equal to h bar to some power of w, multiplied by g to some power of x, multiplied by c to some power of y, and kb to some power of z. We now need to find the values for w, x, y, and z. Let's then substitute our m, l, t, and theta values for each of these constants. So we now get L equals m to the w, L to the 2w, t to the -w, multiplied by L to the 3x, m to the -x, t to the -2x, times L to the y, t to the -y, times L to the 2z, m to the z, t to the -2z, theta to the -z. Now, this side of the equation isn't going to change for the different Planck units. This is always going to be the same. Now, this L here is really L to the power of 1. We don't write it in, but it's there. So let's now go and come up with some equations for each of L, m, t, and theta. We're going to separate out the values and develop some equations that's going to help us to work out the values of w, x, y, and z. First then, let's look at the powers of L. On this side of the equation, we have L to the 1, so that's 1. And that equals 2w plus 3x plus y plus 2z. Now let's consider the m's. We've got no m's on this side of the equation, so this is 0. And so 0 equals w minus x plus z. Now the t's, and again I've got 0 on this side of the equation, and that equals minus w minus 2x minus y minus 2z. And finally the theta values, and again we've got 0 on this side of the equation, and we only have a minus z on this side. This means therefore that z equals 0. We can then get rid of the z values from our equation because they're equal to 0. In fact, the z values are always going to drop out to 0 unless I have a non-zero term on this side of the equation. From this equation here, we can see that w minus x equals 0. So therefore, w equals x. That means whatever value we work out for w, x has got to have the same value. This also means that in these equations up here, I can substitute in x for w. So wherever I have a w, I can put an x. This means that this equation becomes 1 equals 2x plus 3x plus y. And this other equation becomes 0 equals minus x minus 2x minus y, which gives us 1 equals 5x plus y, and 0 equals minus 3x minus y. We can now solve these as simultaneous equations. If we add the equations together, it gives us that 2x equals 1. So therefore x is a half. And if x is a half, W is also a half. We can now substitute in our values of x and w into this equation, and we get that minus y equals 3 over 2, and so y therefore equals minus 3 over 2. This means that our Planck length equation is now LP, that's the Planck length, equals h bar to the half multiplied by g to the half multiplied by c to the minus 3 over 2, which then is the square root of h bar times g divided by c cubed. So that gives us what we know is the equation for the Planck length. Shall we move on? I'm going to go a little faster for the next two until we get to temperature, otherwise this is going to be a really, really long video, and I'm sure no one wants to watch me do maths for half an hour. Let's move on to Planck mass, and now we want to see what powers of h bar, g, c and kb equals mass. Let's write m to the 1 as we know, and the terms on the right hand side are the same as before, so I'm just going to put them there. Going and looking at the m, l, t and theta individually like we did last time, we're going to start with the m values. So because I've got m over here, I've got m to the 1, so that equals 1 equals w minus x plus z. For L, 0 equals 2w plus 3x plus y plus 2z. For T, 0 equals minus w minus 2x minus y minus 2z. And for theta, 0 equals minus z. Z therefore equals 0 again, and so we can get rid of the z terms. From this equation we can work out that w equals 1 plus x. So we can now substitute this into these two equations, and it gives us 0 equals 2 plus 2x plus 3x plus y. So therefore 0 equals 2 plus 5x plus y. And from this equation we get 0 equals minus 1 minus x minus 2x minus y. So 0 equals minus 1 minus 3x minus y. And again we can now solve these as simultaneous equations by adding them together. And we get that 0 equals minus 1 plus 2x. So 2x equals minus 1, so x equals minus a half. W is 1 plus x, so w is 1 minus a half, so w is a half. And substituting x into this equation, we get 0 equals 2 minus 5 over 2 plus y. And that gives us 0 equals minus a half plus y, and so y is a half. This gives us mass equals h bar to the half, g to the minus half, and c to the half. And that gives us our equation of Planck mass, which is mp, Planck mass, equals the square root of h bar c divided by g. Let's do the same for time. So now t to the 1 equals some power of h bar, g, c and kb. And this gives us this equation, again with the right hand side being exactly the same as before. We know that z is going to equal 0, so I'm going to ignore it from the start. For t, 1 equals minus w minus 2x minus y. For L, 0 equals 2w plus 3x plus y. And for M, 0 equals w minus x. From this last equation here, we can see that w equals x. And we can substitute this into the t and L equations. And it gives us, therefore, 1 equals minus x minus 2x minus y. So this means 1 equals minus 3x minus y. And also 0 equals 2x plus 3x plus y. So 0 equals 5x plus y. Again, we can solve these as simultaneous equations, and by adding the equations together it gives us 1 equals 2x. So therefore x is a half, and because x and w are the same, w is a half. Substituting these values into this equation, we get 0 equals 1 plus 3 over 2 plus y. So y is minus 1 minus 3 over 2, so y is minus 5 over 2. Putting this all together then, we get that Tp, Planck time, h bar to the half times g to the half times c to the minus 5 over 2. So Planck time is the square root of h bar times g divided by c to the 5. Finally then on to theta. So to start with, we have theta to the power 1. And that equals the same right-hand term as we had before. Now this time, taking our theta values, we've got 1 equals minus z. This then means that z is minus 1. For L, 0 equals 2w plus 3x plus y plus 2z. For M, 0 equals w minus x plus z. And for T, 0 equals minus w minus 2x minus y minus 2z. We know that z equals minus 1, so we can substitute minus 1 into these equations. And it's going to give us for L, 2 equals 2w plus 3x plus y. For M, 0 equals w minus x minus 1, so therefore x equals w minus 1. And for T, minus 2 equals minus w minus 2x minus y. We can now substitute our value of x, which is w minus 1, into the equations. So substituting it into this equation here gives us 2 equals 2w plus 3w minus 3 plus y. So therefore 5 equals 5w plus y. And minus 2 equals minus w minus 2w plus 2 minus y. So minus 4 equals minus 3w minus y. And here we've got another simultaneous equation to solve. So adding these equations together, we get that 1 equals 2w. And so w is a half. And because we know that x is w minus 1, we therefore know that x is minus a half. Plugging these values into this equation here to find y, we get that 0 equals 1 minus 3 over 2 plus y minus 2. Therefore, minus y equals 1 minus 3 over 2 minus 2. Minus y is then minus 5 over 2, so y is 5 over 2. So Planck temperature is h bar to the half, g to the minus half, c to the 5 over 2, kb to the minus 1, which gives us the square root of h bar times c to the 5 divided by g multiplied by kb squared. Now I have to admit, when I first did the maths, I was really confused why kb didn't come out to be minus 2. And as we can see, it's minus 1, isn't it? And it actually took me ages going over the maths trying to find out where I'd gone wrong. And it was only later when I was driving that it suddenly hit me that because I'm taking a square root here, I have to square kb to get it to equal the 1 that I was looking for. So that's the maths that underpins the Planck units. So now hopefully you know where those values come from. Those values that we've looked at were the fundamental values that were the first to be recorded. There are some derived units which I'm probably going to look at in future because I enjoy it. But my head is hurting a little bit now from the maths. So I'm going to get into my time and space machine and take a little break. And for now, and until next time, thank you for watching.